people. Who's here? Let me see, who's been using Go more than 3 years? Okay, hey, you all came to the front, that's cool. More than 1 year? Okay, who's like a newcomer, just come to learn? Okay, well that's great, that's great. Well, hopefully you can learn some stuff, and we want to welcome you to the community. It's a great thing. You like the shirt, by the way? A little bit, okay. Let me see. So, let me see if this is working. I woke up at like 4 a.m. a few weeks ago with just a very vivid impression of how this talk should go. And it went like this. The first slide says Go, because I'm going to be talking about Go. You're here at GopherCon. It's good. It's all good. The second slide says large, because I'm going to be talking about Go in the large, building large systems, large things. And the third slide was this one. So I don't know. I don't know what the lesson is here. Don't follow your dreams. What am I talking about? I wrote it down. Yeah, okay. So it's coming up on the 10th anniversary of Go being released as 1.0. So it didn't change much in those few months. So it's pretty much 10 years at being at the 1.0 general availability level. So I wanted to kind of think about where have we been? How people are building larger and larger systems. That's kind of the theme of my talk. How do we learn those things? And also, how do we build the foundation for the next 10 years? Okay. No, that's going the wrong way. It's funny though. Yeah, guess how many? Anybody know how many Go developers are there in the world, according to popular estimates? Well, apparently it's somewhere around 1 to 2 million. I looked this up. So you're part of a big gang. That's, I think, quite impressive. Okay. Yeah, right. Okay, and the other thing I found this statement from, it's actually in the Go brand book, if you believe there is such a thing. Go is designed for creating software at scale and running software at scale. So I find that interesting because creating is a human thing. It's about the people that do the creating. And running is about the technology. So we'll try and bear that in mind as we go through. Okay. What do I mean large system? So you build them large probably to handle a lot of work, but also built out of a lot of different parts. You need to, if you're handling a lot of load, a lot of diverse things. So I'm not talking about kind of one front end just randomly spreading the load across a bunch of back-end servers that are all the same. That's relatively simple, all talk to one database, something like that. Could build a large system that way. But when you go much bigger, breaking it down, different functions, things operating on many different machines. And the other thing you have to, once you've got many machines going, you have to cope with failure. At any moment, one of those machines is potentially going to crash or fall over or whatever. And so that's very much something you have to deal with all the way through working with large system. Nice picture. I want to talk about scaling up. So this is very, well, to people that kind of work in the area, this is a pretty familiar picture that as you, so on the x-axis, this is kind of as you split the work into more and more pieces, and the y-axis is how much faster it goes. You get a kind of a tailing off. So this is, as I say, this is pretty famous. It has a name, Amdahl's law. Oh, by the way, I've got a page of links at the end, so you don't have to kind of memorize everything that I said. Yeah, so you get this kind of gradual tailing off, and the numbers don't matter. You know, the numbers will be different depending on how you built the system, but the pattern of scaling, kind of reaching a limit, is there. Now, when you scale up more, those of us who've been there, this is also the pattern. If you take the same thing and scale it way more, it'll actually slow down again. I think this is less familiar, but hopefully kind of intuitive, that the effort of organizing all the different pieces starts to get more than the benefit of splitting it into more pieces and doing more work in parallel. So another kind of way of looking at that, if you have 4 things to talk to each other to try and reach agreement, there's like 6 conversations they can have. The 5 things, there's 10. Be careful drawing this picture. Rob Pike might appear. Anyway, the number of conversations grows with the square of the number of things that are communicating with each other. And this is kind of in that picture, that the slowdown is a kind of a quadratic effect as things get bigger. Now, I mentioned earlier that we're talking about the technology, but we're also talking about the people. So this happens in your people organization. The more people that have to kind of agree the way forward, the slower that's going to be. So that's I think, an important lesson. And it's a little bit sad. It'd be nice if everyone could just agree at every step of the way. But it's a bad idea, because it's going to slow down your progress. Okay. So what's the largest Go program, or what's the largest Go program you know about? I don't know all the Go programs. Maybe you have the largest one. What do you think? A couple of people said Kubernetes. Well, it so happens I had prepared that. This is the number of lines of code in Kubernetes plotted in the Git repo, plotted over the time since the repository started. And this is excluding third-party vendored code, excluding blank lines, excluding purely comment lines, and excluding code-generated code, of which there's a lot in Kubernetes. So the bits that I reckon the humans typed in is heading up towards 1.5 million lines of code. I put myself on this picture as well. This is my first commit to Kubernetes back at the beginning of 2016, and I thought it was pretty damn complicated then. yeah, about 300,000 lines of code. It was pretty hard to get my head around. But that's certainly one of the bigger ones. The things that I work on, so I work at Grafana Labs. I work on these systems primarily, and they're backend systems. They're all written in Go. They're all open source. Cortex stores metrics. Loki stores logs, and Tempo stores traces, just like distributed tracing. So between them, they come in somewhere like 300,000 lines on the same metric, excluding third-party code. Although there is quite a lot of code shared with Thanos, so which we work on. So I don't know. Anyway, so it's not as big as Kubernetes, but it's still, and they're all related. They all kind of share an architecture and share ways of working and ways of scaling and so on. So this is why I'm interested in this topic, because it's my job. And we have, well, Grafana Labs has something like 200 people coding in Go. It's grown a lot. Although this is kind of the back end of the Grafana cloud system. There's also the whole front end Grafana dashboard, which is separate. Anyway, let's go back and talk a bit about kind of ways of building, and also ways of learning how to build these systems. So this is kind of the same picture I put up before. This figurative large system split up into many pieces. So at the core, or maybe the core of one bit of it, there'll be some kind of coordination. Somebody keeping track of what's going on, making decisions, and so on. And remember, this has to carry on in the face of failure. So how do we do that? Well, you can go look up the sort of patterns for these things. The things like quorum voting and write-ahead logs and real leader election. Things that you would use in the very core of a system like that. It's really tricky to get right, that stuff. But the good news is somebody's already done it for you. In fact, several times. In Go, you can use console, which has all those techniques in it, the kind of the raft algorithm and the write-ahead log and all that stuff. etcd is another one. They're written in Go, so you can actually vendor the code into your system, which we do as an option in Cortex and so on, or call them as a service. So yeah, that's pretty good story at the core of the thing. So next, thinking about how do these things talk to each other? Well, I think from what I see, the dominant there's two main choices that people make. They either send JSON over HTTP, or they use gRPC, and typically that's a protobuf encoding. So again, those things are really well served in Go libraries. I think there's some other patterns. There's a talk on NATs, which I think is tomorrow, which is kind of another way you might have the parts talking to each other, the messaging system. So that might be interesting. So anyway. Then you, once again, thinking about failures. So imagine we have maybe these pieces over here. They're making requests, and they perceive a failure. They retry. What can happen is the retry. Even if you go too fast with your retries, you can kind of overload the system they're talking to. And this is very vivid for me because it happened on Friday afternoon. We had a meltdown in Grafana Cloud, essentially because a bunch of customers' endpoints were retrying calls very quickly. It basically looks like a DDoS attack. Anyway, so you have to be careful when you're coding up retries. So one of the things we've done just very recently, we took a lot of the code in those systems, Cortex, Loki, Tempo, and we created a new library we called DS-Kit, Distributed Systems Kit. So, number one, we did it because it's this thing about lots of people having to agree. We kind of pull it out into a central place, and there's less kind of tripping over each other. But it's Apache licensed, so other people can use it, other people can contribute. What is in DS-Kit? Well, a bunch of I'm not going to go through the list, but a lot of the things I've been talking about, sharding, this word we use, breaking things up into pieces so they can run across multiple machines. So you can do that kind of at random, just spread the load out to some endpoint at random. But if it's got some kind of state or caching or something like that, you want to send the same type of request, maybe the same customer to the same endpoint each time. You want to do that consistently. So there's a technique called consistent hashing, where we spread the load to the same endpoints each time. If you add endpoint, if you scale up, then some of the load moves to the new endpoints, but most of it stays where it was. If you scale down, the same thing happens. So this is very tricky to get right. And that's we pulled that out of Cortex into DS-Kit. That's very much at the core of how we scale those services. And we're inside Grafana Labs, we're running on hundreds of machines. We also have customers running on hundreds. I think they're heading up into the thousands of machines. It's a bit scary, to be honest. But anyway, so on my theme of building large systems and also kind of learning from what other people have done, that's a new option. I have to apologize. It's not very polished. If you go find it on GitHub, it's very much in a state of evolution. There are basically no docs, so sorry about that. But anyway, it's out there. It might be useful. Right, rounding off. Looking forward, what do I think are opportunities to improve the state of the art, to build things that. Well, I want to mention tomorrow's keynote. Andre is talking about really a radically different take, I think called Encore. So that'll be very interesting. I'm kind of down a level where we're still just kind of typing in code and trying to get it to work. So I think, number one, RPC. The JSON encoding, protobuf encoding, they're not very efficient. And I haven't seen, I've seen a lot of attempts at doing better, but I haven't seen a truly great one. If you've got one, come see me. But I think there's an opportunity there for a better RPC paradigm, web service, whatever, to come along and make that work better. Can we do better with sharding? I mentioned, I spoke in detail about some of the things we do, but it's still quite hard to manage. You have to have quite a lot of knowledge, and it can go wrong in kind of weird and unexpected ways. So I think there's opportunities there to do that better, neater, cleaner, more automatic. Can Caching, yeah, I didn't even mention, I mean, caching is one of these things where you set yourself up to not do the work, which is nice. So I see a lot of people using memcached Redis. They're very powerful, very popular. There isn't really a Go, a Go cache on a par with those. Maybe there could be. The client libraries for memcache and Redis in Go aren't that great. So there's opportunities there. And I wonder whether generics will help there, because if you've ever used a cache in Go, the pattern tends to be the sort of interface to brace, just an opaque object that you then have to cast to the thing you wanted. And there's overheads in boxing up objects that you already know what the type is, but it has to kind of turn into an opaque thing in the cache. Anyway, generics would let us have a typed cache. Maybe that would work better. Maybe that would be a cool thing to do. So yeah, that's kind of looking to the future. Go is 10 years old. Go has been open source for 12 or so years. All the things I talked about are open source. There's fantastic opportunities to get involved and create things, build your own things. And so I just want to leave you with make something exciting happen. Thank you.